Okay, here's this is for 5 through 7 for this net force 1. Net force just means sum of all forces or unbalanced force. Net force, if you're wondering what that word net is, like net profit or whatever, it means just like after you've done all the plussing and minusing and all the canceling out, what's left. So net force is the same as unbalanced force. All right, so anyway, let's get into number 5. So I'll do that on a separate sheet here. A 70-kilogram skydiver jumps out of an airplane. You know, I should have made this a helicopter, so you didn't have to worry about the sideways motion. I hope that wasn't confusing. So we're just talking about basically dropping somebody from very high up. Immediately after jumping, how large is the skydiver's acceleration? So right after they jump, the only force acting on them is the force of gravity on the skydiver from the entire Earth. And they're 70 kilograms, so that's going to be 700 newtons. And then if you wanted to find the acceleration, then unbalanced force is equal to winners minus losers. There's no losers, there's just this all by itself. So that's what I would call the unbalanced force equation. And then their mass times acceleration is equal to the force of gravity, which is 700. So their acceleration is 10 meters per second squared. But we knew that anyway from Unit 4, right? That's like free fall. Or Unit 4? Unit 3? I guess Unit 3, right? So we know that free fall acceleration is 10 meters per second down. No surprise there. The reason it says in Part A, immediately after jumping, if you're wondering, like, what's up with that? What's up with the immediately? It's so before the skydiver starts to pick up speed, the faster you go, the more air you're crashing into and the more air resistance there's going to be. So the idea there is before there's any air resistance. Okay, so Part B, upon reaching a downward velocity of 100 miles an hour, there's 300 newtons of drag in resisting the diver's motion. So now the force diagram, of course, gravity doesn't care. Still 700 newtons there. Now there's this force of drag on the skydiver from the air, and they're not equal to each other. This one's 700 and they told us here that this is 300. Okay, so what would the unbalanced force equation be here? I've got winner minus loser, so that's force of gravity minus force drag. So mass times acceleration equals 700 minus 300. So the acceleration is about 5.7. And the acceleration is always going to be in the direction of whatever's winning. So if we wanted to just make sure that we know that, it's down. All right, that's number 5. Number 6. Got a 900-kilogram car, exerts 5,000 newtons of traction force. That's like the forward force on a level road while being opposed by 1,000 newtons of friction. Friction and drag forces combined. Okay, so let's draw that force diagram. I think I have enough room over here. My car is going to be going to the right, so there's force of traction on the car from the road, and we're given that that's 5,000. There's a force of gravity on the car from the entire Earth, and that is the mass times 10, so that's 9,000 newtons. Don't be one of these people now that forgets to multiply that by 10. That's a bummer if you do that, or forget to do that, or whatever. The support force or normal force on the car from the road, do we know what that is? Sure we do. This car is not moving in the up-down direction, so definitely those are balanced. And then we're being told here that we have 1,000 newtons of friction and drag, whatever combined. I'm just going to call that a friction force on the car from friction and drag forces combined. I guess I'll call that from the air. I'm not going to fuss at you about what you put there. And that's 1,000 newtons. Write a net force. Sorry, I don't want to confuse things. I wish I had said unbalanced there. Unbalanced force equation means the same thing. Okay, unbalanced force equals winner, force of traction. There's no K in traction. Why did I do that? I'll just abbreviate it, track, minus the force of friction. So calculate the acceleration of the car. So the mass of the car times acceleration is equal to traction minus friction, and that gives me an acceleration of about 4.4 meters per second squared. All right, I pushed some buttons on my calculator to do that. All right, number 7, we got ourselves a ramp situation here. It's a slide. So the first thing I need to do is make my dotted line here in the direction of the slide. And then the second thing, this is going back to our force diagram skills from Chapter 4, or Unit 4. There's the kid, and gravity, of course, not caring about anything. Force of gravity on it's a child, so we'll do a C for child. Gravity doesn't care what's going on. 30 kilogram child, so it's going to be 300 newtons of gravitational force there. Okay, now everything else that I do is going to be lined up this way. So here's my other axis. And what else do we have? I do have some friction. On the child from the slide. And there's 160 newtons of that. And there is going to be a support force. But actually, you know, before I drew that in there, probably the next thing I should do is do my X and Y to get here. Just like you're plotting a point, going from here to here. There's your X and there's your Y. And where is my 55-degree angle? So you got to think a little bit about this. The 55-degree angle is going to be here. The better you make your picture, the easier it's going to be for you to tell which angle is which. But for this kind of ramp problem, if you break this up and go X, Y, it's going to be down here at the bottom. If you broke it up the other way, then it would be up there at the top. Remember, there's stuff in geometry about this angle is equal to this one because these are parallel, and those are called alternate interior angles or something like that. So for us in physics, if you draw your lines, try to avoid making things just look like 45 degrees. Then angles that are a little bit bigger than 45 will look a little bit bigger, and then our general rule will just be angles are equal to each other if they look like they're equal to each other, and that's going to serve us just fine. But if you have 45-degree angles, then it looks like all the angles are the same, so you got to watch out for that. So that's where my 55-degree angle is. And now this is 300, so I need to do my sine and cosine business here. Make sure that I am in degree mode. I am. So I need to do 300 times the opposite, that's cosine, of 55 degrees. That gives me 172 newtons there. And then 300 times the sine. Oh, sorry, I messed that up, didn't I? Cosine's the adjacent one. This is the 172. And this is going to be 245, 246, let's say, if we round to the nearest newton. 246 newtons. That's that and that. And that makes sense. 55, this other angle, if you wanted to, that just has to add up to 90, right? Because that's 90, so that'd be 35 there. So this should be smaller than this. The bigger angle has to look at the bigger side. So that all seems good. If this is 300, 246, 172, I look at those, it looks like that makes sense. And how about my support force? Well, this kid is going down the slide this way and not moving in this direction. So this, the up and the down, have to balance each other. I'm saying up and down according to the way I have things tilted now, right? So up and down, those are balanced. So this support force has to be 172 newtons. Right? Okay, and then that's a nice force diagram there. We got all the numbers in there. Write an equation for the forces on the child parallel to the slide and find the net force on the child. So that's in the direction of the slide. So unbalanced force is equal to this right here. Now, I don't want to put numbers in this equation yet. This is the one that's just kind of the description of the forces. This was the cosine, sorry, the sine opposite. That was the sine component of that angle. So I'm just going to write it like that. That was that force of gravity times the sine of the slide angle, minus the force of friction. Right, so again, these are balanced, so they're not involved in the unbalanced force equation. So I have this winner minus this loser. That's my forces in this direction. So there's that. And then calculate the child's acceleration. I don't know what these little things are, by the way. There's some kind of like formatting character, so just ignore those. Sorry about that. L-sep, line separator? I don't know what that is. Something like that. So let's see. Unbalanced force is equal to mass times acceleration. Kid's mass is 30 times acceleration is equal to force of gravity times sine 55. That's this. 246 minus the force of friction is 160. So time to do math. And got about 2.9 meters per second squared. If you're thinking to yourself, whoa, that was really hard. Well, that's just about as hard as these get. There's one more little layer of difficulty that we could add into this in terms of what we can do with friction. But that's really pretty much about as hard as these get. So that was your first crack at one of those. So don't sweat, at least not yet.